everyone, my name is Ikuemuya-Ojo, and today I'll be introducing you to the Ikuemuya-Ojo's theory of relativistic mass. If you are not a physics student, the concept of relativistic mass might be new to you. When we talk of relativistic mass in physics, it's just the mass an object can assume when it is traveling at a very high velocity. Not the normal velocity we are used to, but the velocity close to the speed of light. In discussing relativistic mass, we'll be using a factor called the Lorentz factor. The Lorentz factor is denoted by gamma. Gamma is equals to 1 all over root 1 minus v squared all over c squared, where v is the velocity the object is traveling with and c is the speed of light. Before now, the only existing theory of relativistic mass was given by Einstein. Einstein gave this theory just to explain how a body of mass will behave in relativity when traveling at a velocity close to the speed of light. He also used it to explain why objects with mass cannot attain the speed of light, cannot travel with the speed of light. No matter how fast you run, or no matter how fast a car or a rocket travels, it cannot attain the speed of light, because it was given by the theory of relativistic mass. And Einstein states that in his theory of relativistic mass, that when an object of mass is traveling at a very high velocity, it becomes heavier. So this heavy mass it attains will not make it attain the speed of light, because more energy, infinite energy, will be required to give it momentum to attain the speed of light, which cannot be provided. But Ikuemuya-Ojo came up with another theory. They find Einstein's theory to be non-realistic. Before I discuss Ikuemuya-Ojo's theory with you, I would like to state the mathematical proof of Einstein's theory of relativistic mass. In Einstein's theory of relativistic mass N is equals to the rest mass m naught all over root 1 minus v squared all over c squared. It can also be written as gamma m, where m naught is the rest mass. If you notice from this formula now, if the velocity of the object v is equal to the speed of light, we have relativistic mass m to be equals to m naught all over square root of 1 minus c squared over c squared. C squared cancels c squared over 1. So we have m naught all over 0, which is equals to infinity. So Einstein states that the relativistic mass of a body will become infinity when the object attains or is moving close to the speed of light. Ikuemuya-Ojo find this unrealistic because relativistic mass is a subject under quantum physics, and quantum physics deals with small particles. So discussing that, saying that a fast moving object its mass becomes infinite when it is moving to the speed of light is unrealistic. Take for example, we all use motorcycle when traveling. When you are on a bike and the motorcycle is moving very fast, although that is a non-relativistic velocity, do you feel heavy or light? The answer that you feel light. So Ikuemuya-Ojo came up with another theory to state that while objects travels at high velocity, their mass become light and tends to 0, but cannot be equal to 0. Because if the mass equals to 0, the law of conservation of energy, the law of conservation of matter will go against. Law of conservation of matter says matter can never be created nor destroyed. So, but if the mass of the object, the object is traveling at a very high velocity, the mass will be tending towards 0, but cannot be equal to exactly 0. Because if it equates to exactly 0, that means the mass with that matter has been destroyed, which goes against the law of conservation of matter. So the Ikuemuya-Ojo theory of relativistic mass states that as the object of mass travels close to the speed of light, the mass becomes lesser, become lighter, tends to zero, but does not exactly equal to zero, because if it equals to zero, the law of conservation of matter will go against. And that is why no object can travel by the speed of light. Only object that has no mass, where m is equal to zero, can travel with the speed of light. So in this case, with Ikuemuya-Ojo theory of relativistic mass, when the object travels at a speed close to the speed of light, the mass becomes close to zero, but cannot equate zero, so it cannot travel by the speed of light. Mathematically, the Ikuemuya-Ojo's theory of relativistic mass can be written as relativistic mass m to be equals to square root of 1 minus v square all over c square m naught, where m naught is the rest mass. So if the velocity of the object is close to the speed of light c, the relativistic mass m will be equals to square root of 1 minus c square over c square m naught. C square will cancel c square, so the relativistic mass m will be equals to 0. So that shows that no object can travel at the speed of light. And when the object, if at all any object travels at the speed of light, its relativistic mass does not become heavy, just like what Einstein says, but it becomes 0. That is why a car that is moving at a very high speed, any small teeth can turn the car upside down, because the mass is become reduced, so it can be affected by any small change in parameters in the environment. Even in communication, radio wave communication, if a wave is being transmitted at a very high frequency, which you can say at velocity, little things in the atmosphere such as dew can affect the radio signal. That is why your DSTV, when rain is falling, your DSTV will lose signal, because they are transmitting at SHF, super high frequency. So as the frequency increases, the vulnerability of the signal increases. So also with the Ikuemuya-Ojo theory of relativistic mass, why it is more realistic. As the body travels close to the speed of light, its mass reduces. It does not become infinite as what Einstein said. It reduces to close to 0, but can never be equal to 0, because if it is equal to 0, the law of conservation of matter will go against, and no physical object can go against the law of conservation of matter. So this is the Ikuemuya-Ojo's theory of relativistic mass. You can go online, Google Ikuemuya-Ojo's theory of relativistic mass, and you read the published paper. Thank you.